NFPA 70, the National Electrical Code, requires all electrical systems to be properly bonded and grounded to ensure safety and prevent electrical shock. Article 250.118 specifies acceptable equipment grounding conductors, including metal raceways, armor of cables, and equipment grounding conductors. Article 250.118 subsections 2, 3, and 4 allow the use of metal raceways as equipment grounding conductors only under specific conditions. These conditions are the raceways installed in accordance with Article 300. The raceway is metallic and electrically continuous, meaning there are no breaks or non-metallic sections. The raceway is bonded to the grounding electrode system at the service equipment and any other required points. Outlet grounding requirements are also specified in the NEC. Article 210.7 requires all 120 volts, 15 amps and 20 amps receptacles to have a grounding conductor. Article 250.146 A1 specifies that grounding conductors must be run with the circuit conductors and connected to the grounding terminal of the receptacle. A contractor's argument that conduit alone is an acceptable equipment grounding conductor is valid under specific conditions. Firstly, the conduit meets the requirements of Article 250.118 subsections 2, 3, and 4. Secondly, the panel and transformer are properly bonded to the grounding electrode system. For proper bonding and grounding, consider the following. There is no ground wire coming to the panel. The transformer is not bonded to the building. There are no ground wires pulled to the outlets and no ground pigtails to the boxes. For safety and code compliance, it is recommended to install a ground wire to the panel and bond the transformer to the building. Additionally, ground wires should be pulled to all outlets and connected to the grounding terminal of the receptacles. While conduit can be used as an equipment grounding conductor under certain conditions, it is not an acceptable substitute for a dedicated ground wire in many cases. It is essential to have a properly bonded and grounded electrical system to ensure safety and meet code requirements. Now let's delve further into the specifics of grounding and bonding according to the National Electrical Code. Grounding refers to connecting the electrical system to the earth, providing a low impedance path for fault currents to return to the source. Bonding, on the other hand, involves connecting non-current carrying metal parts of the electrical system together to create an electrically conductive path. The main purpose of grounding is to protect people from electric shock. In the event of a fault, such as a live wire coming into contact with a metal enclosure, the ground provides a path for the fault current to flow back to the source, tripping a circuit breaker or fuse and energizing the circuit. Without proper grounding, the metal enclosure could become energized, posing a shock hazard to anyone who touches it. Bonding ensures that all metal parts of the electrical system are at the same electrical potential. This minimizes the risk of voltage differences between different metal parts, which could also create a shock hazard. The grounding electrode system is a critical component of the grounding system. It consists of one or more grounding electrodes that are connected to the earth. Common types of grounding electrodes include ground rod, metal water pipes, and concrete encased electrodes, often referred to as U for grounds. The grounding electrode system must be properly sized and installed to provide a low impedance connection to the earth. The size of the grounding electrode conductor, which connects the grounding electrode to the electrical system, is determined by the size of the service entrance conductors. The equipment grounding conductor is another important part of the grounding system. It is a conductor that connects the non-current carrying metal parts of the electrical system, such as metal enclosures and equipment frames, to the grounding electrode system. The equipment grounding conductor provides a path for fault currents to flow back to the source, tripping a circuit breaker or fuse. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device protecting the circuit. Bonding jumpers are used to connect different metal parts of the electrical system together. For example, a bonding jumper is used to connect a metal water pipe to the grounding electrode system. Bonding jumpers must be properly sized and installed to provide a low impedance connection between the metal parts. The National Electrical Code specifies detailed requirements for grounding and bonding in Article 250. This article covers a wide range of topics, including grounding electrode systems, equipment grounding conductors, bonding jumpers, and grounding of specific types of equipment. It is essential for electrical contractors and installers to be familiar with these requirements to ensure that electrical systems are properly grounded and bonded. Now let's talk about some specific scenarios related to grounding and bonding. In the case of a new panel installation, it is crucial to ensure that the panel is properly grounded. This typically involves connecting a grounding electrode conductor from the panel to the grounding electrode system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. In addition to grounding the panel, it is also important to bond the panel enclosure to the equipment grounding conductor. This ensures that the panel enclosure is at the same electrical potential as the other metal parts of the electrical system. When installing receptacles, it is important to use receptacles that have a grounding terminal. The grounding terminal of the receptacle must be connected to the equipment grounding conductor. This provides a path for fault currents to flow back to the source if a fault occurs in the appliance plugged into the receptacle. In some cases, metal conduit is used as the equipment grounding conductor. However, this is only permitted under certain conditions. The conduit must be electrically continuous and properly connected to the metal enclosures and equipment. It is also important to ensure that the conduit is not damaged or corroded, as this could compromise its ability to conduct fault current. If metal conduit is not used as the equipment grounding conductor, a separate equipment grounding conductor must be installed. This conductor is typically a green insulated wire that is run along with the circuit conductors. The equipment grounding conductor must be properly sized and connected to the metal enclosures and equipment. Transformers also require proper grounding and bonding. The transformer enclosure must be bonded to the equipment grounding conductor. In addition, the neutral point of the transformer, if any, must be grounded. The grounding of the transformer neutral provides a stable reference point for the electrical system and helps to prevent voltage fluctuations. When working with electrical systems, it is always important to follow safe work practices. This includes wearing appropriate personal protective equipment, such as safety glasses and gloves. It is also important to energize the circuit before working on it. This can be done by turning off the circuit breaker or removing the fuse that supplies power to the circuit. Before working on any electrical equipment, it is important to verify that the circuit is de-energized using a voltage tester. A voltage tester is a device that indicates whether or not a voltage is present in a circuit. If the voltage tester indicates that a voltage is present, do not work on the equipment until the circuit has been de-energized. Grounding and bonding are essential for electrical safety. By following the requirements of the National Electrical Code and using safe work practices, it is possible to minimize the risk of electric shock and electrical fires. Consider additional points to reinforce the understanding of grounding and bonding. Firstly, understanding impedance is important. Impedance is the total opposition to current flow in an alternating current circuit and is measured in ohms. A low impedance ground path is crucial for quickly clearing ground faults. The lower the impedance, the greater the fault current, and the faster the overcurrent protective device, such as a circuit breaker, will trip. Secondly, the role of the ground fault circuit interrupter, or GFCI, must be taken into account. While grounding provides a path for fault current, a GFCI is designed to protect people from electric shock by detecting even small imbalances in current. GFCIs should be used in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Thirdly, surge protection is important for equipment. Grounding and bonding also play a role in surge protection. A properly grounded system can help to divert surge currents, such as those caused by lightning strikes, away from sensitive electronic equipment. Surge protective devices, or SPDs, should be installed to protect valuable equipment from damage caused by surges. Fourthly, about grounding electrodes. The NEC specifies different types of acceptable grounding electrodes, including ground rods, metal water pipes, and concrete encased electrodes. The choice of grounding electrode depends on site conditions and local requirements. In some cases, multiple grounding electrodes may be required to achieve a low-impedance ground path. Fifthly, about the importance of documentation. Proper documentation of grounding and bonding systems is essential for future maintenance and troubleshooting. Documentation should include the location of grounding electrodes, the size and type of grounding conductors, and any other relevant information about the system. Sixth, inspection and testing are important as well. Grounding and bonding systems should be inspected and tested regularly to ensure that they are functioning properly. Testing should include measuring the impedance of the ground path and verifying the continuity of grounding conductors. 7. The use of listed equipment matters. Always use electrical equipment that is listed by a recognized testing laboratory, such as Underwriters Laboratories or all. Listed equipment has been tested and certified to meet safety standards. 8. Be aware of local amendments. Local jurisdictions may have amendments to the NEC that are specific to their area. It is important to be aware of these amendments and to comply with them. 9th, regarding training and qualifications. Electrical work should only be performed by qualified and trained personnel. Working with electricity can be dangerous, and it is important to have the knowledge and skills necessary to do the job safely. 10th, think about the future. As technology advances, electrical systems are becoming more complex. It is important to stay up to date on the latest grounding and bonding requirements and best practices. By understanding the principles of grounding and bonding and following the requirements of the NEC, it is possible to create safe and reliable electrical systems. Also, remember that grounding ensures a safe path for fault currents, while bonding creates an electrically equal environment. Both are critical for electrical safety. Now, consider the practical implications of these concepts. Imagine a scenario where a metal enclosure of an appliance comes into contact with a live wire due to damaged insulation. Without proper grounding, the enclosure becomes energized, and anyone who touches it is at risk of electric shock. However, with a properly grounded system, the fault current flows through the grounding conductor back to the source, tripping the circuit breaker and quickly de-energizing the circuit, preventing injury. Similarly, imagine a situation where two metal enclosures are not properly bonded together. A voltage difference can develop between the enclosures, creating a shock hazard if someone touches both enclosures simultaneously. Proper bonding ensures that all metal parts are at the same electrical potential, eliminating this risk. Also consider the importance of grounding in sensitive electronic equipment. Electronic devices are susceptible to damage from voltage surges and electrical noise. A properly grounded system provides a path for these disturbances to dissipate, protecting the equipment from damage. In addition to safety and equipment protection, proper grounding and bonding also improve the performance of electrical systems. A stable ground reference helps to minimize voltage fluctuations and ensure reliable operation of electronic devices. To summarize, grounding and bonding are essential for electrical safety, equipment protection, and system performance. By understanding the principles of grounding and bonding and following the requirements of the NEC, it is possible to create electrical systems that are safe, reliable, and efficient. It's worth reiterating the importance of adhering to local electrical codes and regulations. These codes are designed to ensure the safety of electrical installations and may vary depending on the jurisdiction. Always consult with a qualified electrical inspector or engineer to ensure that your electrical work complies with all applicable codes. Let's explore some specific scenarios and address some common misconceptions related to grounding and bonding. Firstly, consider the case of a subpanel installed in a detached garage or shed. The NEC requires that a separate grounding electrode system be installed at the subpanel. This typically involves driving a ground rod into the earth near the subpanel and connecting it to the grounding busbar. The grounding electrode system at the subpanel provides a local ground reference and helps to protect against ground faults. Secondly, consider the myth about grounding to cold water pipe. While metal water pipes were once commonly used as grounding electrodes, this practice is now discouraged by the NEC. This is because plastic water pipes are increasingly being used, and a plastic section in the water pipe can interrupt the ground path. If a metal water pipe is used as a grounding electrode, it must be supplemented by another type of grounding electrode, such as a ground rod. Thirdly, consider the confusion about grounding and neutral conductors. The grounding conductor and the neutral conductor are separate conductors that serve different purposes. The neutral conductor carries current back to the source under normal operating conditions, while the grounding conductor provides a path for fault currents. In a properly wired system, the neutral conductor and the grounding conductor are only connected together at the service entrance. Finally, consider the importance of using the right size of grounding conductors. The size of the grounding conductor is determined by the size of the circuit conductors. Using a grounding conductor that is too small can compromise the safety of the electrical system. Always consult the NEC or a qualified electrician to determine the correct size of grounding conductors for your application. By understanding these specific scenarios and dispelling common misconceptions, you can gain a deeper appreciation for the importance of grounding and bonding. Now let's talk about the role of technology in advancing grounding and bonding practices. Smart grounding systems are emerging that use sensors and monitoring devices to continuously monitor the performance of grounding systems. These systems can detect potential problems such as corroded grounding conductors or loose connections, and alert maintenance personnel before they lead to safety hazards. Also, advanced modeling and simulation tools are being used to design and analyze grounding systems. These tools can help engineers to optimize the design of grounding systems for specific applications and to ensure that they meet all applicable codes and standards. Furthermore, new materials are being developed for grounding conductors and electrodes. These materials offer improved corrosion resistance, conductivity, and durability, leading to more reliable and long-lasting grounding systems. As technology continues to evolve, it is likely that grounding and bonding practices will continue to advance, leading to safer and more efficient electrical systems. Let's discuss some practical tips for maintaining grounding and bonding systems. Firstly, visually inspect grounding conductors and connections regularly for signs of corrosion or damage. Replace any damaged or corroded components immediately. Secondly, test the continuity of grounding conductors periodically to ensure that they are providing a low impedance path for fault currents. Thirdly, tighten all grounding connections regularly to ensure that they are secure and making good electrical contact. Fourthly, protect grounding electrodes from physical damage. Install them in locations where they are not likely to be struck by vehicles or other equipment. Fifthly, keep grounding electrodes free from vegetation and debris. This will help to ensure that they are making good contact with the earth. By following these practical tips, you can help to ensure that your grounding and bonding systems are functioning properly and providing the protection that they are designed to provide. Now, let's consider the ethical implications of proper grounding and bonding. Electrical contractors and installers have a responsibility to ensure that their work is safe and complies with all applicable codes and standards. Cutting corners on grounding and bonding to save money or time is unethical and can put people's lives at risk. It is important to prioritize safety and to do the job right, even if it means incurring additional costs or taking more time. Also, electrical inspectors and engineers have a responsibility to enforce electrical codes and to ensure that electrical installations are safe. They should not be pressured to approve substandard work or to overlook violations of the code. Ultimately, proper grounding and bonding is not just a technical issue, it is also an ethical issue. It is about protecting people's lives and ensuring the safety of our communities. In conclusion, grounding and bonding are fundamental to electrical safety and system performance. A solid understanding of the principles, adherence to codes, and ethical practices are crucial for all involved in electrical work. From understanding impedance and GFCIs to the use of advanced technologies and ethical considerations, we've covered a comprehensive overview of grounding and bonding. Remember to always prioritize safety, consult with qualified professionals, and stay updated on the latest advancements in this critical field.